So this is regularization part 2, still looking at linear algebra. But now, after we very often apply nonlinear regularizations. And as we'll see, regularization is very important in feature engineering. Feature engineering is the basis for applied machine learning, and in fact, for much of data science in general. So in general, our goal is the best approximation of some kind of a true model. Our model that we're going to use is a parameterized model. Y, the response, is a function of X, the features, given some parameters. We use data to obtain the best estimate of the weights, and that leads us to a fitted model. So the model F hat is still F of the features, but now with a fixed best estimate of the weights. We're going to have bias, and notice we have a true model in the bias. This one is incredibly complex, and in general, we never know the true model. We should probably just assume that. It includes how fast the wind is blowing on Mars, what the kangaroos are doing in Australia. It's far beyond what we can do with just a data set. And we also have mean squared error, and we've proved that mean squared error is the square of the bias plus the variance all over the data plus some irreducible error. In other words, the total error is the squared bias plus the variance plus the irreducible. That leads to this diagram where we have the model complexity on the horizontal. And notice that if we have a very complex model, we're going to get overfitting. But our model has to be complex enough to approximate this true model and should also extract as much information from the data as possible during the fit. In other words, learning. So for example, suppose we have data but no model. We want to have a curve to fit to this following data set. And here's the test data. Here they are together. So we're going to do regression. Given the data, estimate the weights of a model for which y hat equals f of xi is a best approximation of y sub I. This is also known as curve fitting. We can do this, say, for example, with k nearest neighbors. Each predicted y hat is the average of the y sub I of the k nearest neighbors to xi, yi. And here's our k nearest neighbors fit. Notice if we zoom in, if we take an arbitrary point on our fitted curve, then its value comes from the average of its, in this case, 10 nearest neighbors. There are many other regression methods. For example, random forest regressor looks like this. A gradient boosting regressor looks like this. The extra trees regressor looks like this. The bagging regressor looks like this. But most people would regard these as examples of overfitting. Again, going back to our bias variance trade-off diagram. And notice that we have very high model complexity. We're going to get overfitting. So in general, however, if we're looking at this kind of data and trying to fit it with a curve, we're probably assuming we have some very smooth signal, and the noise is what's making it look like this. So here's our original smooth signal we actually used, and we added noise to it. So often the real question is, how do we separate the signal from the noise? Smooth means differentiable. Polynomials are differentiable. So let's use multilinear regression for curve fitting. So our model here is some polynomial, and D is going to be much larger than whatever the final model is going to require. And we're going to have polynomial features. So we've got our F and our Y matrices. We're going to do this kind of multilinear regression to find our optimal weights. But how do we control these parameters? For example, can we set some of them equal to 0? Or maybe close to 0? And if so, which ones? How do we know? This takes us to the concept of regularization. So in convex optimization, we minimize some function of the weights subject to constraints. And that includes constraints on the parameters. Constraints such as L1 constraints, where the L1 norm is less than delta. And that defines a region in my space. So in this case, L1 regions, or L1 balls in some sense, are these diamond-shaped things. If you have an unconstrained minimum and you force it, the solution to be in this region with a constraint, then the parameters will be forced to zero that are in the region. So we'll get a new answer, not quite the unconstrained minimum, but one which has some zeros for weights. We also have L2 constraints. So these are usually just traditional ball type constraints, which means that our final solution is inside the region and it's closest to whatever the unconstrained minimum is, or where it occurs. Now, a theorem in convex optimization proves that an L1 constraint forces some of the parameter values to be zero. So then we look at our Lagrangian, and here I'm going to use alpha as our Lagrange multiplier. And notice we've got this Lagrangian. If we can find where the Lagrangian is equal to the derivative of Lagrangian is zero, then we've solved our original problem subject to our constraint. Now, because these are inequality constraints, our alpha here is going to have to be positive. Now, solving the Lagrangian is in some sense equivalent to solving the original problem subject to the constraints. And we could have simply said, well, what if we had just added some alpha norm W1 to the objective itself? So we, instead of solving a Lagrangian, we actually have this new objective, h of W plus alpha, the one norm of W. So that final term is called a regularization term. And you can prove a theorem in convex optimization that solving the Lagrangian and minimizing with this new objective are in some sense equivalent. So how do you choose the best alpha greater than zero? Well, we use the AIC information criterion. So here's multilinear regression. And we're going to include some constraints on the weights. So here's my L1 constraint, which means I'm minimizing the norm, Euclidean norm squared of FW minus Y, plus my regularization term alpha norm W1. And this is called Lasso regression. My L2 constraint, I'm minimizing with now a 2 norm added on squared. And this is called ridge regression. And I could use both, in which case it would be called elastic net regression. And I would be minimizing with both regularization terms. And then you determine the best alpha and beta via cross-validation or AIC. And we'll do both in this video. So here is my data, but no model. I want to find the best weight by doing this multilinear regression, but I add this nonlinear one norm regularization term. So I can use a process in scikit-learn called Lasso IC, which uses AIC to identify the model whose alpha minimizes the AIC. It's not hard to use because everything in scikit-learn you use in exactly the same way. Notice that we're going to have d equals 10, so we're going to have 10th degree polynomials. And we're going to create the polynomial features, which will give us our f. And then we're going to do a lasso regression using the AIC, and it's going to proceed over a series of possible alphas and pick the best one based on the AIC. Now notice that we're going to consider the intercepts separately. So this polynomial features matrix is not going to have the column of ones. And instead, we're going to let Lasso figure out what the intercept is. This is a general practice that I don't know if it's preference or what, but I tend to use it. I tend to let the methods figure out what the intercepts are. So here is our possible alphas. These are all the alphas that were used by the Lasso Lars IC. And you'll see that we get a minimum at 2.335 times 10 to the negative sixth. So that is our best alpha, and that's the one we'll use for our lasso. Now, once we have our best value for alpha, the lasso itself produces coefficients. And here you can see that all but 3 of the coefficients, 3 of the 10, are equal to 0. And this is my W star at this value alpha star. So here are my best estimates for my W's. And I can actually write down the curve that best fits the data. It's 2.955 plus 2.005x. That's the W1 star, plus 4.282x squared minus 8.597x to the fourth plus 3.930x to the seventh. Here is my data. Here is my curve fit model. And here's my actual signal. And notice that the way I got this signal, just so we can do some comparison, was I took 2x plus 3, which I've written as 3 plus 2x, and then I added a 1/2 5x squared, and then if you look at its Taylor polynomials, then it's the 3 plus 2x plus 2.5x squared minus the 10.417x to the 6, and so on and so forth. So the Lasso Lars did a pretty good job of the first 2 coefficients. Not so great on the next 3. So let me look at this more theoretically. We have a function that's convex mapping r sub k to r, and its derivative at some w star is 0, which means that for all alpha or a and b in rk, we can define a function h of xy, which is just a function of x and y, and that's h of ax plus by plus w star, and it has to be bowl-shaped. So it has to look something like this. What that means is if you take level curves, if you take horizontal cross sections of this bowl shape, then your unconstrained minimum will be the lowest level, and then you'll start getting ellipse-like curves centered at the argmin. So here are some level curves of this function. Now, a regularizing constraint is actually a region. It's a subset of RK, which usually has properties like it's closed and bounded and things like that. So in our case, we were looking at the L1 constraint, and you're going to get some kind of a diamond shaped. In K dimensions, it will be a diamond shape in any horizontal slice or any planar slice you take through the origin. And then the level curves are going to grow till they reach a vertex that's in the region. And notice once they hit a vertex, then at that vertex, most of or many of the coordinates at a vertex are equal to 0. Now, this is intuitive again, but we can say more. These constraints decrease model complexity. So notice that by forcing something to be in a region, we have a less complex model. So that means the unconstrained minimum is often for a highly complex model that often overfits. But the regularized minimum is the closest point in the region to the unconstrained, and in the L1 case often gives us some subset of zeros for the weights. So suppose we have this lasso problem. Notice that we've got the norm, one norm of the weight W at the end, and that's equivalent to simply taking the sum of the absolute values of the weights themselves. But we can actually replace those absolute values by these mu's, and then we can minimize such that these norms, these absolute values have to be less than or equal to these individual mu values. That gives us more variables, but convex optimization theory, the Kruskal-Tucker conditions, will imply that a non-empty subset of the mu1 to mu k must be 0 when you reach a minimum. And if the mu's are 0, then the corresponding weights have to be 0. There's also a rich theory for ridge regression. We can actually find its solution in closed form. Can write that in terms of the Moore-Penrose pseudo-inverse, although it's not necessary. So let's look at an example. We had this image, data, but no model. So are we done? We finished here? No. We only used the numerical information in the data to get this. Regularization in this process was just a naive reduction in model complexity. But there's always more to data than just numbers, and there are always smarter ways to regularize the weights. So let me just give you kind of a trivial example. This data we assumed was a smooth signal plus noise, and we want to separate the signal from the noise. We'll assume that the noise has a mean of 0. So if you add up all the deviations from the curve, you get 0. And it's a pretty defensible assumption in almost every application. So if you take a moving average, then as you pass over the data, you're going to be averaging over the noises. And those averages are going to be 0. So here we've averaged, and notice now the noise is closer to 0 because these are averages of noises over this moving average window. Now we repeat the Lasso regression, and here's my fit, and here's my original signal. Notice by using the fact that this data corresponds to X having an order because it's the real line, that allows us to do a moving average with respect to that order and get a better model. So our data has structure. The X coordinates of the data are ordered. The order matters. Differentiability depends on the ordering of R. So why would you talk about rates of change if you don't have a firm concept of what it means to change from one point to another on the real line? And regularization and preprocessing, as you see here, they often work together to predict and exploit structure in the data. So let's look at an example. So here we have data in 2 dimensions, and we're going to apply logistic regression to it. Well, it's not linearly separable, so there's no line that we can draw that's going to divide the class 0 from class 1, but we can do some feature engineering. We can generate a bunch of polynomial features. Here we do that. We're using degree 4 here, and that's going to give us these polynomial features from the original set of data. Notice that I also did a min-max scaling before I did the polynomial features. So here is my logistic regression, and guess what? It's perfect. Everything's perfect. The area under the curve is perfect. The area under the precision recall curve is perfect. The confusion matrix is perfect. The accuracy is perfect. Everything is perfect. 1.0. But let's look at the decision surface, because this perfection is not evidence of a great model. It's evidence that we overfit the data. So here is my decision surface for my model. It's weird. It overfit the data. Notice we got this weird region over here on the far left. Well, where did that come from? There aren't any data points over there that are in class 0. It created a structure or topology the data does not have. We don't see this structure in the data. It doesn't generalize to the test data. So if I've got my test data, which looks like this, then notice the topology that I'm predicting here, the structure with my decision surface, it's not a good it doesn't generalize to more sampling and more data. And this is for 4th degree polynomials. What about for degree 5? Well, we get another topology. So the weights also become arbitrarily large in magnitude. So here are the weights. There are 65 polynomial features for 10th degree polynomials, and notice how big they are. So notice we're going from negative 10 to the fourth to 10 to the fourth. So that's negative 10,000 to 10,000 with these weights. But some of the weights are relatively close to zero. Massive changes in magnitude in the weights here. Here we look at it logarithmically, but you can see the same thing. So much of the data is absolutely magnitudes 1,000 to 10,000 of these coefficients. They're big, they're huge. So let's use logistic regression with regularization. Ideally, the degree of the polynomial model is really high because we want the actual model to be a special case. But such models have necessarily very high complexity. Overfitting allows perfect fits, but produces non-generalizable models. So we regularize the coefficients in our logistic regression to lower the complexity of the models by adding constraints to binary cross entropy. So here is our problem of minimizing cross entropy for logistic regression. And I add an L2 regularization term. Notice that I don't have a parameter in front of the regularization. Instead, I have a C in front of the objective. So that means I've got C times my objective plus my regularization term, rather than H plus some regularization term. And as C gets larger and larger, alpha gets closer and closer to zero. Why do we use the C approach? Well, especially in the past, we found that the C approach with existing software and approaches allowed faster implementations of the algorithms used to estimate the parameters. So they're equivalent, and you'll see both in scikit-learn and in general, either putting a C in front of an objective and letting it become bigger and bigger, as opposed to letting alpha be smaller and smaller, or vice versa, letting alpha be bigger and bigger, corresponding to C becoming smaller and smaller. So here is our logistic regression, and notice now I'm using the logistic regression CV. It allows me to put in a bunch of values for C, and it will use cross-validation to pick out which C value is the best for my L2 regularization. So I don't get perfect anymore, but I get pretty close. But I do get a decision surface that's generalizable. So now I have something that will generalize to the test data. And notice that it misses a few, but it misses about the same number that it missed in the training set. The coefficients from this L2 regularization, well, they're much more tame. So notice that they go from about 0.1 to about 10, rather than for the classical logistic regression going from 10 to 1,000 to 10,000. Remember, I'm using the log scale here. So what about an L1 regularization? Well, now we add an L1 term. And notice we again have the C out in front. The cross entropy function is convex, so some subset of the weights will necessarily be zero. And if I combine the two, I get what's called the elastic net regularization of logistic regression. So here again, my logistic regression CV, but now the penalty is L1. And again, it's not perfect, but most of the coefficients are zero. Most of those weights are zero. That allows me to not only have a decision surface that generalizes to test data, but also to predict a decision boundary with just a few terms. So we have to invert the initial scaling. So remember, we actually did a min-max scaling. And when we invert that, we get these values. And that gives me a decision boundary that looks like this. So it's an ellipse. We could also have done elastic net. Notice you get a better score, but I actually would prefer either L1 or L2, but I usually don't use both. You might think you get something, of value, but what you really get is that combining L1 and L2 is not always the best of both worlds. I think you would be better off creating an L1 model and an L2 model and then using some kind of an ensemble, a stacked regression or something like that. So regularization is very important. Good models in data science depend heavily on both feature engineering and model building. Both can lead to overfitting, which often leads to poor generalization. If you pre-process, then you must apply metrics. That's something we emphasized earlier. But if you engineer features, you must regularize. Why? To guarantee that every aspect of a final model is informed by the data and not contrived by the modeler. You want the model to reflect the information, numerical and structural, of the data and not wild assumptions coming from the outside.